Okay, we can officially start and then everybody else can join in the meantime. Welcome to our third session out of our DMAT webinar mini-series titled The Future of Material Manufacturing, Embracing Open Source Digital Solutions for SME Growth. My name is Elish Tereva and I'm going to be hosting this session today. This is a part of a four-part mini-series. The focus of our sessions is technically to provide you with the latest developments, trends, challenges, and opportunities in material manufacturing in the field of digital solutions, and more specifically, open digital solutions for SMEs. These sessions are 40 minutes long, and we are here to provide you with the latest and most relevant information. We already had two sessions up until now. On the 21st of November, we were speaking about digital trends and challenges across the material value chain. Then on the 5th of December, we went on the full scale of the material value chain, starting with material data management, operationalization, and life cycle assessment. And today, on the 11th of December, we're going to be speaking about predicting material behavior and advancing material design. Our previous sessions are already recorded and available on our YouTube channel. In case you have missed them, you can go there and watch them. We also have one final session, which is going to run next week on the 17th of December. And there we're going to be focusing on digital simulation in material manufacturing. We will be speaking about numerical modeling for industrial SMEs, optimizing manufacturing processes through simulation, and enhancing process control via digital twins. Now going back to the session for today, predicting material behavior and advancing material design, let me introduce you to our speakers. First, we have Lukas Morand, who is a developer and researcher at Fraunhofer Institute for Mechanics of Materials. Lukas is our resident keynote speaker. He was here with us for the first two sessions, now for the third session as well. We will definitely miss him for the fourth session where he is not going to be present. Then we also have Yannis Papadimitriu, who is an AI and materials science researcher at the Center for Research and Technology. This is also the coordinating organization for the DMAT project. We have with us Leonardo Cosma, who is a simulation engineer at CETMA, and myself. Apart from me moderating, at the end, I'm also going to share with you a brief opportunity on how you can further collaborate with us and our excellent solutions. Regarding the agenda, first we will start with managing material modeling and design information, leveraging semantic technologies presented by Lukas. Then we're going to move to material properties and behavior prediction, digital solutions to reduce trial and error approaches presented by Yannis. And then we'll go to digital assessment and comparison of material properties by Leonardo. And as I said, I'm going to take 2-3 minutes of your time to be speaking about our upcoming call for early adopters. Now, without further ado, I'm giving the floor to Lukas.
Afternoon, everybody. I'll talk today about managing material modeling and design information and leveraging semantic technologies. First of all, I would like to start with why we do materials modeling and design and why it is important and about the challenges of materials modeling and design. And yeah, I guess that most of you have already been in contact with modeling and design of materials, at least modeling and simulation, I guess. And why we do this or why you do that is typically you want to predict the behavior of materials of your product. In terms of, for example, safety and life cycle, so you don't need to do experiments, or you can do this before experiments, and you can optimize your materials and products before you produce them. And optimization, here we are in the design of materials. Optimizing or designing materials, meaning that you tailor your materials to specific requirements, which are typically you want to enhance the performance of your materials and products, some efficiency requirements or sustainability. But materials modeling and design is quite challenging, I would say. I can also talk here from my own experience. So materials modeling is really a big field with a lot of material models existing, and material modeling approaches are enhanced and new material modeling approaches are developed, I would say, more or less on a daily basis. So we have really a vast amount of materials models out there, and this is very hard to overview. So if you want to apply or develop a new material model to your product, so you can model and simulate the behavior of the material of your product, you really need a lot of experience in the fields of material science, modeling, and simulation. And this to get this experience is very hard. So typically, I would say you need lifelong or need a lot of years of working in material science to get a good overview of about material modeling. And I think even if you're experienced, I bet you would not say that you know all of the materials models out there. So this is a big challenge and a big barrier for people to apply the right material model to their product. So that is one thing, and the other thing is you cannot just take a material model and apply it to or use it to model your behavior of the product. You need access to experimental data. You need to gather experimental data on your own. You need to experiment the material that you have and test it out and then fit the material model to it. And also you need to understand how it behaves. And you need tools to analyze the experimental data that you have so you find the right material model for your application. And last but not least, if you do all this on your own, it's really, really hard. So you need a community for knowledge exchange that support you in, as said, identifying the right material model, simulation approach, and apply it to your product. Next, I would like to introduce you to the materials design framework, which is a toolkit we have developed. And I will first introduce this and then talk about the semantic technologies that I said in the beginning later. The materials design framework, this is a framework that supports you and guides you along your process to find the right material model and to model and simulate your product or process that you have at hand. So it consists of three components: an exploration component, and correlation component, and a materials relation component. And these three components, they basically give you the path how you can go on. So first, you find the relevant data that is describing the material and its behavior. When you have found such data, then you can analyze and derive information from it using the correlation component. And at the end, based on your findings, you can use the material relation component that provides you knowledge about the right material model. And all of these components are connected to one other DMAT toolkit that I introduced in the last webinar, which is the DMAT Cloud Materials Database, which is a modern data management solution based on semantic technology. So here is where the semantic technologies come into play. And all of these components, they use the CMDB under the hood to store data, to get data, and to analyze data from it. And on the next slide, I have summarized the advantages that these semantic technologies brings to this component. So the CMDB stores data in a fair manner, so it's findable, accessible, interoperable, and reusable. The data stored there can be enriched with a meaning, so we can add relations to certain data points to get a better understanding of the data. And in that manner, also we can link data sets and represent complex workflows that we often also have in materials modeling. And the MDF, the materials design framework component I'm presenting today, leverages these semantic technologies. So it can, with the fair data management, it can access data of different sources in one application. So independently of what data you have, experimental data, simulation data, different sources, different formats, you can store everything in the CMDB, and the MDF can access all of that and work with it seamlessly. Using the relations, I said, we get a better understanding of the data. And also this allows us for storing or getting materials modeling knowledge using the materials design framework. And the next, I will go in detail, or a little bit more in detail into the three components, and will show you what they can and what you can do with them. So with the exploration component, this is a basic component that you need to explore the data sets in the CMDB, so you can locate specific data sets and find information in the CMDB. You can, for example, find data sets of certain types, or you can find linked data sets, and so on, using a simple navigation, using a simple free text search, for example, but also using Sparkle queries. Sparkle queries, however, are quite complex. So if you want to find, if you want to go for a deeper search, we are about to implementing a large language model-based search. This is our vision for this component, that you really can search the CMDB database together with a chatbot, so that you can, for example, ask the chatbot some questions to summarize some tests that have been conducted on textile material, for example, and then the chatbot will answer you depending on what he finds in the CMDB. Once you have found information there, and this gets us to the next component, you can apply the correlation component. And here I brought to you a little video that Ellie will start now. In the video, you can see that you can easily interact with the data sets that can be found in the CMDB and identify, for example, correlations. So this is what we can see in that video. You can see now, for example, a simple correlation matrix, and then after having checked the correlations, you can also visualize your correlations. But there are also other functionalities like mapping data to a 3D space. So if you have high dimensional data, you can analyze it. And you can also at the moment find similarities between selected data sets, which is also quite helpful, and which takes advantage of the relations or the linked data that we have in the CMDB. And last but not least, we have the materials relation component. The materials relation component is an ontology-based system for storing and retrieving knowledge about materials modeling. So this tackles the challenge that the field of materials modeling is quite huge, and then there are a lot of materials models existing out there. And we aim here to provide a simple framework where the community can fill this framework with knowledge. They get an easy interface to register new material models, and these material models are saved in an ontology. And then the user can determine appropriate material model for observation they made during experiments. So you specify what you have observed in the experiments, and the component will help you to find the correct material model. And also for the next step, we aim that the component will help you to identify the best simulation tools, because as with the material models, we have also a lot of simulation tools out there, and it's really difficult to find out which simulation tool is the best for your material model. So all in all, I want to summarize the materials relation component. As we have seen, we have three components, which is the exploration component, correlation, and materials relation component, that guide you along your process to find and apply the right material model for your application or for your product. The MDF facilitates material modeling, information provision, so in terms of data, and also in terms of organizing in-depth knowledge about materials modeling approaches.
Thank you, Lucas. Before I move to the next presentation, something that I have missed to mention in the beginning. As you know, we have a Q&A chat box. I saw that some of you have orientated already with it and have already started asking some questions. In case you have any, please post them there during the course of our presentation. We will try to answer them. And now I'm giving the floor to Yannis, who is going to be speaking about material properties in behavior prediction, digital solutions to reduce trial and error approaches.
Thank you. Thank you, Eli. So let us start with the challenge in materials development today. It's a real challenge, but we will use a fictional example. So there is Sarah Chen, a senior materials engineer at her company. Like many in her field, she's tasked with developing new lightweight materials for electric vehicles. That's really common nowadays for the past few years. Here's the challenge though. Each iteration of her work takes 3-4 weeks or maybe more of lab time. Cost is in the thousands, and she needs to balance 6, which is a lot, different material properties simultaneously. This fictional example represents the traditional approach to materials development that many of us are familiar. It's a continuous cycle of preparing samples, running the experiments, analyzing results, and modifying any parameters as we go on. Each round hoping to get closer to our target parameters and properties. This trial and error approach, while thorough, is becoming increasingly unsustainable as of late, as in today's competitive environment where development time and costs are critical factors. And this is where the digital solutions come in, which I'm going to talk about next. Machine learning and artificial intelligence in general are buzzwords for the past few years. They're changing how we approach materials development lately, though. Instead of relying solely on physical experiments, we can now use data-driven approaches to predict target properties and optimize processing parameters. This means we can explore thousands of potential combinations in minutes rather than months in some cases. We're seeing companies reduce their development cycles while simultaneously discovering better solutions that they would have found through traditional methods, if they could have found them. The key isn't eliminating experiments entirely. That's actually really hard to do, but it's about making the experiments smarter and more targeted. So to map uncharted waters, so to speak. Next slide, please. To make this digital transformation work, we need actually 3 crucial elements. The first one is robust and ample data, and its management needs to be actually even more robust. This means not just collecting the data, but organizing them in a way that captures any relationships between materials, processes, and properties. Because nevertheless, AI and data-driven approaches, what they do is they give us the latent relationships between the data that a human cannot really see without going to the lab. Second, we need advanced analytics capabilities that can handle the complexity that is abundant in material science. Third, we need to integrate domain knowledge, because material science isn't just about numbers. It's about understanding the physical and chemical principles behind that. And the solution space in most real world cases is so vast that without domain expertise, even data-driven approaches would be limited. What's particularly exciting is how these components work together. So when we combine machine learning with domain expertise, we can ensure our predictions not only fit the initial data that we were supplied, but also make scientific sense. And this hybrid approach is what makes our modern digital solutions so more powerful than trial and error. So this brings me to our solution, the DMAT Materials Modeler, or DMM. We've designed Materials Modeler to address exactly these challenges we have been discussing so long. What makes it unique is its comprehensive approach. From the moment you input your data, it helps you structure them, analyze them in a way that's specifically optimized for material science, and it's intuitive for both a data scientist and a material scientist. It understands that materials parameters, process parameters, and performance metrics needs to be treated differently, and it's built to handle the real world messiness of materials data, because in real world cases you don't have perfect, pristine, curated data. You have missing data. You have complex relationships between the data. You have a lot of dimensions, and in most cases you have not abundant data as it is with open data in the few cases. So let me walk you through how Materials Modeler works As you can see in the next slide, in the flowchart that we have here, we start with data input, where the user can tag the parameters based on their role and their nature, materials properties, process parameters, and target parameters or performance metrics. This structured approach is crucial because it allows the system to apply appropriate processing methods to each type of the data. The system then moves through processing and analysis stages, where it handles missing data, performs exploratory data analysis, identifies key features, and does the filtering of the outliers depending on the user's domain expertise and selection. What's particularly powerful is how it builds and optimizes models specifically for your material system. The workflow is designed to be both rigorous and intuitive, ensuring that you get reliable results without needing to be an actual data science expert. Finally, let me highlight some of the more advanced capabilities of the materials modeler. Beyond just prediction, because prediction is something that given enough data or given clean enough data, let's say, most of today's tools can't be competitive about it. But beyond just that, beyond just the prediction, it can perform reverse engineering, which is actually really handy in the real world. Meaning, if you have a target property in mind, it can suggest the optimal processing conditions or optimal initial material parameters to achieve it. This, of course, needs to be supplied with enough data to do that in order to map those uncharted waters I was talking about earlier. But it gives this ability to the user, and it also integrates with open source AI assistants, allowing for natural language interaction with your own data while running in a secure and private environment, whether you are using local or cloud resources. Summarizing, the materials modeler represents a new generation of digital tools that are making materials development faster, more efficient, more streamlined, and I would say more innovative. Having said all that, thank you for your attention and happy to take any questions.
Thank you, Yannis, for your presentation. Now we are moving to the final part regarding the DMAT solutions presented by Leonardo. He's going to be speaking about digital assessment and comparison of material properties.
Thank you, Ellie. In the previous two talks, my fellow DMAT colleagues have brilliantly exposed how different digital solutions can help companies in material design and material predictions. Now I will try to close the loop because my colleagues have spoken about how to explore data to generate new knowledge and to generate, at least digitally, new materials. But there is, of course, the necessity to obtain data from somewhere. Of course, we can rely on data from manufacturers' datasheet, private repositories, but we know that at the very end, when talking about materials, all the knowledge and wisdom that we can build comes from physical data obtained via physical testing. The traditional material design processes rely heavily on physical testing, and of course this tends to be slow, costly, and inefficient. A traditional trial and error approach involves developing a particular solution, planning a physical testing campaign, evaluating the behavior of the material, and then repeating the cycle until the result is good enough. Analytical models can help us in this travel, but we are only at a low level. We are just testing components of materials to find a suitable candidate. We still have to pass to the upper level of designing and testing components of parts. Digital solutions can help us in two ways. The first one is pointing the way in the right direction to improve our result. And to this aim, the previous two toolkits are valuable and I'd say intriguing tools. The second way to help us is to reduce or ideally to eliminate the physical testing required to assess each specific material solution during the material design process. And here is exactly where the DMAT materials designers comes to the point. It is a digital tool that we bring to the users to allow the digital assessment of material properties via the so-called virtual testing approach. The idea is to use computer simulations to virtually reproduce the physical testing and to predict the behavior of materials. What are the benefits that a tool like the DMAT material designer can offer with the digital assessment of materials and materials properties? Well, of course, the first thing that comes to mind is the reduction of time and cost of the material development process. We use digital assets, we can concentrate a bunch of evaluation in a very short time, we save a lot of material, we can reduce the time to market. We can also have a deeper insight into material behavior. With virtual testing, we have greater control over the inputs, the testing conditions, the material characteristics, so we have full control on what we are testing. Secondly, we can literally see into a material. We can virtually look inside the internal structure and better understand what we observe outside in terms of behavior and macroscopic properties. And finally, it is easier to find optimal solutions. We can efficiently explore the design space because we have control on the inputs and we have less limit of the number of tests. And we can more easily include different disciplines, different kinds of assessment like cost or environmental impact in our workflows. The use of numerical calculation has been originally applied to the upper levels of the pyramid that you can see on the right to understand the mechanical behavior of parts or their components and simple elements. The use of tools like the DigiMat Material Designer is equivalent to extending this approach to the base level, the coupon level, where the calculations involve just small specimens of material and the output that we're looking for are the material properties. So speaking more in detail of the Material Designer, on the next slide, this is a tool which executes virtual tests to assess the material properties of the advanced materials. It is focused on composite materials and can support different kinds of matrix and reinforcement materials. The tool uses two different calculation approaches for the virtual testing. Finite element calculations that reproduce digitally the physical tests, or analytical models that are incorporated to offer to the user a fast but less accurate solution for an initial screening. It is a complete cloud solution. The user has access to the Material Designer using the web browser. There is no need to install anything because all calculations are executed externally, remotely. Now, starting from the next slide, I will show you a typical workflow to calculate the properties of a composite using this toolkit. As a first thing, the user should define the base materials, the matrix and the reinforcement. Typically, the matrix is polymeric and the reinforcement is glass or carbon, but we will support other types of materials like natural fibers, for example. The second step on the next slide is to define the internal microstructure, which is how internally the two phases are arranged. We support different types of microstructures, and I will say more on this later. The final step is to define the composite, which is typically a stacked material made of different layers with different orientations. Once every information is fed to the toolkit, the user just pushes on the play button that you can see in the background, and after some time, the results are available in the user interface, as shown in the next slide. And it is possible to visualize one material at a time or to compare different solutions. Now, I will just give you a brief recap of all the features of this toolkit. First of all, we include we support different kinds of possible microstructures. We started with short and long fibers, but we are implementing also textile reinforcement with different types and geometries. And we also plan to support thermal calculations, so it will be possible to assess also the thermophysical properties of materials. About data analysis, it is now possible to make graphical comparisons between different solutions, as I've shown you in the previous slide, but we are also adding a parametric studies capability. So the user will have the possibility to plan simulation campaigns and visualize input and output relationship. Finally, the toolkit can operate alone, but it can be linked and connected to other DMAT solutions. We plan to have the option for the user to export data to the DMAT Cloud Material Database, a semantic storage solution that we are developing in DMAT project. And moreover, if data from the material designer is sent to the Cloud Material Database, as Lukas has shown you before, it is possible to use the material design framework to analyze those data. So the user can rely on one toolkit for the data generation, which is the material designer, and another one for advanced data analysis, which is the material design framework, for example. We are also implementing a software development kit that will allow users to interact programmatically with the material designer via scripting without the web browser interface. So the interested users will be able to deeply integrate the functionality of the toolkit into their own digital tools. And this is it for the material designer. Thank you.
Thank you, Leonardo, and thank you all for those informative and very insightful presentations. And now that our audience know about the DMAT solution, so we'll partially know, because as you know, in our previous session, we were talking about our data management and assessment solutions. Today, we're talking about material prediction and modeling. And in our next presentation, we're going to be talking about our simulation and optimization suite and toolkits. We actually want to introduce you to an opportunity via which you can collaborate with us. This is our upcoming call for early adopters. And I'm going to very briefly share with you what it is all about and when you can apply for it. The call is going to be launched next week on the 17th of December, aligned with our final webinar session. And I would say that the aim is very obvious. We would like to interact with end users and early adopters of the solutions. We would like to receive your targeted feedback based on which we're going to further develop our solutions in response to the actual industrial needs coming from our interaction with you. When you can apply, once the call is open, it's going to accept applications for a total duration of 2 months. And afterwards, we're going to have a brief assessment on the organizations that are suitable to interact with us. And this collaboration is going to last for up to 2 months as well, for the period within March and April. What you're going to get from this collaboration, of course, apart from early access to our cutting-edge solutions, you're going to have an assigned expert depending on the solutions that are of your interests and based on your needs, who is also going to not only support you in understanding the best way to optimize and integrate the solutions according to your needs, but also is going to further explore and support you in optimizing your digitalization strategy connected to your operational and business needs. In addition to that, we're also going to provide you with further marketing exposure. We're going to create the articles for you according to the collaboration that you're going to establish with us. We're going to position you on our website and much more. How this application process is going to run, as stated on the 17th of December, we're launching this. It is going to be open on the F6S platform. All this information is going to be available on our website. There you're going to have a button, which is directly going to send you to the application form. It is going to be very brief. After you fill it in, this is basically it for you. Afterwards, our experts are going to assess whether your organization is suitable for this short collaboration opportunity. And afterwards, we will get it going. Of course, we're not going to be able to collaborate with all organizations, as we want to really focus our resources and provide as much as effort and collaboration opportunities as needed. But all organizations that are interested to explore the DMAT solutions and are interested in the overall topic of material manufacturing will get direct access to our discussion board, which you can see here on the right side on the screen. There you can ask all your questions, not only related specifically to what the DMAT project and solutions are, but anything related to digitalization for material manufacturing, and we will provide you with a response regarding to that. Also, we're going to be sharing interesting events, both physical and online, and any latest research and opinion articles that are coming within the field. Of course, we're not going to be spamming you, as we want to be targeting only what is relevant for you. So please do send your questions so we can support you in the best way possible. And I think this is my last slide. Yes, this is it in a nutshell. Do not miss our next session next week on the 17th, where we're going to be exploring, as mentioned, digital simulation optimization. We're going to be speaking about digital twins and much more, and we will be launching our open call. Thank you for your time today, and see you next week. Bye.